In computing, eye-SKUZ-ee is an acronym for Internet Small Computer System Interface, an Internet protocol-based storage networking standard for linking data storage facilities. By carrying SCSI commands over IP networks, eye-SKUZ-ee is used to facilitate data transfers over intranets and to manage storage over long distances. eye-SKUZ-ee can be used to transmit data over local area networks, wide area networks, or the Internet, and can enable location-independent data storage and retrieval. The protocol allows clients to send SCSI commands to SCSI storage devices on remote servers. It is a storage area network protocol, allowing organizations to consolidate storage into data center storage arrays while providing hosts with the illusion of locally attached disks. Unlike traditional fiber channel, which requires special-purpose cabling, eye-SKUZ-ee can be run over long distances using existing network infrastructure. eye-SKUZ-ee was pioneered by IBM and Cisco in 1998 and submitted as draft standard in March 2000. Concepts: in essence, eye-SKUZ-ee allows two hosts to negotiate and then exchange SCSI commands using Internet Protocol networks. By doing this, eye-SKUZ-ee takes a popular high-performance local storage bus and emulates it over a wide range of networks, creating a storage area network. Unlike some SAN protocols, eye-SKUZ-ee requires no dedicated cabling. It can be run over existing IP infrastructure. As a result, eye-SKUZ-ee is often seen as a low-cost alternative to fiber channel, which requires dedicated infrastructure except in its FCOE form. However, the performance of an eye-SKUZ-ee SAN deployment can be severely degraded if not operated on a dedicated network or subnet, due to competition for a fixed amount of bandwidth. Although eye-SKUZ-ee can communicate with arbitrary types of SCSI devices, system administrators almost always use it to allow server computers to access disk volumes on storage arrays. eye-SKUZ-ee SANs often have one of two objectives: storage consolidation. Organizations move disparate storage resources from servers around their network to central locations, often in data centers. This allows for more efficiency in the allocation of storage, as the storage itself is no longer tied to a particular server. In a SAN environment, a server can be allocated a new disk volume without any changes to hardware or cabling. Disaster recovery: organizations mirror storage resources from one data center to a remote data center, which can serve as a hot standby in the event of a prolonged outage. In particular, eye-SKUZ-ee SANs allow entire disk arrays to be migrated across a WAN with minimal configuration changes, in effect making storage routable in the same manner as network traffic. Initiator: an initiator functions as an eye-SKUZ-ee client. An initiator typically serves the same purpose to a computer as a SCSI bus adapter would, except that, instead of physically cabling SCSI devices, an eye-SKUZ-ee initiator sends SCSI commands over an IP network. An initiator falls into two broad types. A software initiator uses code to implement eye-SKUZ-ee. Typically, this happens in a kernel-resident device driver that uses the existing network card and network stack to emulate SCSI devices for a computer by speaking the eye-SKUZ-ee protocol. Software initiators are available for most popular operating systems and are the most common method of deploying eye-SKUZ-ee. A hardware initiator uses dedicated hardware, typically in combination with firmware running on that hardware, to implement eye-SKUZ-ee. A hardware initiator mitigates the overhead of eye-SKUZ-ee and TCP processing and Ethernet interrupts, and therefore may improve the performance of servers that use eye-SKUZ-ee. An eye-SKUZ-ee host bus adapter implements a hardware initiator. A typical HBA is packaged as a combination of a gigabit Ethernet network interface controller, some kind of TCP/IP offload engine technology, and a SCSI bus adapter, which is how it appears to the operating system. An eye-SKUZ-ee HBA can include PCI option 1 to allow booting from an eye-SKUZ-ee SAN. An eye-SKUZ-ee offload engine, or ISOE card, offers an alternative to a full eye-SKUZ-ee HBA. An ISOE offloads the eye-SKUZ-ee initiator operations for this particular network interface from the host processor, freeing up CPU cycles for the main host applications. eye-SKUZ-ee HBAs or ISOs are used when the additional performance enhancement justifies the additional expense of using an HBA for eye-SKUZ-ee, rather than using a software-based eye-SKUZ-ee client. ISOE may be implemented with additional services such as TCP offload engine to further reduce host server CPU usage. Target. The eye-SKUZ-ee specification refers to a storage resource located on an eye-SKUZ-ee server as a target. eye-SKUZ-ee target should not be confused with the term eye-SKUZ-ee, as the latter is a protocol and not a storage server instance. An eye-SKUZ-ee target is often a dedicated network-connected hard disk storage device, but may also be a general-purpose computer, since as with Initiators, software to provide an eye-SKUZ-ee target is available for most mainstream operating systems. Common deployment scenarios for an eye-SKUZ-ee target include, storage array. In a data center or enterprise environment, an eye-SKUZ-ee target often resides in a large storage array, such as Pure Storage, HP Left-Hand Store Virtual or 3PAR Store Serve, Equal Logic, Take-All Systems, Nimble Storage, Reduio, IBM StoreWise, Isilon, NetApp Filer, EMCAN S-Series, CX4, VNX, VNXE, VMAX, HDSHNAS Computer Appliance, or Pivot 3 VSTAC. A storage array usually provides distinct eye-SKUZ-ee targets for numerous clients. Software target. Nearly all modern mainstream server operating systems can provide eye-SKUZ-ee target functionality either as a built-in feature or with supplemental software. Some specific-purpose operating systems implement eye-SKUZ-ee target support. Logical unit number. In SCSI terminology, LUN stands for logical unit number. An LUN represents an individually addressable SCSI device that is part of a physical SCSI device. In an eye-SKUZ-ee environment, LUNs are essentially numbered disk drives. An initiator negotiates with a target to establish connectivity to an LUN. The result is an eye-SKUZ-ee connection that emulates a connection to a SCSI hard disk. Initiators treat eye-SKUZ-ee LUNs the same way as they would a raw SCSI or IDE hard drive. For instance, rather than mounting remote directories as would be done in NFS or CIFS environments, eye-SKUZ-ee systems format and directly manage file systems on eye-SKUZ-ee LUNs. In enterprise deployments, LUNs usually represent subsets of large RAID disk arrays, often allocated one per client. eye-SKUZ-ee imposes no rules or restrictions on multiple computers sharing individual LUNs. It leaves shared access to a single underlying file system as a task for the operating system. Network booting. For general data storage on an already booted computer, any type of generic network interface may be used to access eye-SKUZ-ee devices. However, a generic consumer-grade network interface is not able to boot a diskless computer from a remote eye-SKUZ-ee data source. Instead, it is commonplace for a server to load its initial operating system from a TFTP server or local boot device, and then use eye-SKUZ-ee for data storage once booting from the local device has finished. A separate DHCP server may be configured to assist interfaces equipped with network boot capability to be able to boot over eye-SKUZ-ee. In this case, the network interface looks for a DHCP server offering a PXE or BOOTP boot image. This is used to kick off the eye-SKUZ-ee remote boot process, using the booting network interface's MAC address to direct the computer to the correct eye-SKUZ-ee boot target. One can then use a software-only approach to load a small boot program which can in turn mount a remote eye-SKUZ-ee target as if it was a local SCSI drive and then fire the boot process from said eye-SKUZ-ee target. This can be achieved using an existing pre-boot execution environment boot ROM, which is available on many wired Ethernet adapters. The boot code can also be loaded from CD-DVD, floppy disk and USB storage, or it can replace existing PXE boot code on adapters that can be reflashed. The most popular free software to offer eye-SKUZ-ee boot support is IPXE. Most Intel Ethernet controllers for servers support eye-SKUZ-ee boot. Addressing, eye-SKUZ-ee uses TCP for the protocols itself, with higher-level names used to address the objects within the protocol. Special names refer to both eye-SKUZ-ee initiators and targets. eye-SKUZ-ee provides three name formats: eye-SKUZ-ee qualified name, format. The eye-SKUZ-ee qualified name is documented in RFC 3720, with further examples of names in RFC 3721. Briefly, the fields are literal IQN, date that the naming authority took ownership of the domain, reverse domain name of the authority, optional colon prefixing a storage target name specified by the naming authority. From the RFC. Naming string defined by, type date auth example.com naming authority, plus IQN.199.2-01.com example, storage disk arrays SN08675309, IQN.199.2-01.com example, IQN.199.2-01.com example, storage tape 1 /SCSI, IQN.199.2-01.com example, storage disk 2 /SCSI, extended unique identifier, format, OE. EUI 64-bit address, T11 network address authority, format, NOR. NAA 64 or 128-bit identifier, IQN format addresses occur most commonly. They are qualified by a date because domain names can expire or be acquired by another entity. The IEEE Registration Authority provides EUI in accordance with the EUI 64 standard. NAA is part OUI which is provided by the IEEE Registration Authority. NAA name formats were added to eye-SKUZ-ee in RFC 3980, to provide compatibility with naming conventions used in fiber channel and serial attached SCSI storage technologies. Usually, an eye-SKUZ-ee participant can be defined by 3 or 4 fields: hostname or IP address, port number, eye-SKUZ-ee name, an optional CHAP secret, ISNS. eye-SKUZ-ee initiators can locate appropriate storage resources using the Internet Storage Name Service Protocol. In theory, ISNS provides eye-SKUZ-ee SANs with the same management model as dedicated fiber channel SANs. In practice, administrators can satisfy many deployment goals for eye-SKUZ-ee without using ISNS. Security, authentication. eye-SKUZ-ee initiators and targets prove their identity to each other using the CHAP protocol, which includes a mechanism to prevent clear text passwords from appearing on the wire. By itself, the CHAP protocol is vulnerable to dictionary attacks, spoofing, or reflection attacks. If followed carefully, the rules for using CHAP within eye-SKUZ-ee prevent most of these attacks. Additionally, as with all IP-based protocols, IPsec can operate at the network layer. The eye-SKUZ-ee negotiation protocol is designed to accommodate other authentication schemes, though interoperability issues limit their deployment. Logical network isolation. To ensure that only valid initiators connect to storage arrays, administrators most commonly run eye-SKUZ-ee only over logically isolated back-channel networks. In this deployment architecture, only the management ports of storage arrays are exposed to the general-purpose internal network, and the eye-SKUZ-ee protocol itself is run over dedicated network segments or virtual LANs. This mitigates authentication concerns. Unauthorized users are not physically provisioned for eye-SKUZ-ee, and thus cannot talk to storage arrays. However, it also creates a transitive trust problem, in that a single compromised host with an eye-SKUZ-ee disk can be used to attack storage resources for other hosts. Physical network isolation. While eye-SKUZ-ee can be logically isolated from the general network using VLANs only, it is still no different from any other network equipment and may use any cable or port as long as there is a completed signal path between source and target. Just a single cabling mistake by an inexperienced network technician can compromise the barrier of logical separation, and an accidental bridging may not be immediately detected because it does not cause network errors. In order to further differentiate eye-SKUZ-ee from the regular network and prevent cabling mistakes when changing connections, administrators may implement self-defined color coding and labeling standards, such as only using yellow-colored cables for the eye-SKUZ-ee connections and only blue cables for the regular network, and clearly labeling ports and switches used only for eye-SKUZ-ee. While eye-SKUZ-ee could be implemented as just a VLAN cluster of ports on a large multi-port switch that is also used for general network usage, The administrator may instead choose to use physically separate switches dedicated to eye-SKUZ-ee VLANs only, to further prevent the possibility of an incorrectly connected cable plugged into the wrong port bridging the logical barrier. Authorization. Because eye-SKUZ-ee aims to consolidate storage for many servers into a single storage array, eye-SKUZ-ee deployments require strategies to prevent unrelated initiators from accessing storage resources. As a pathological example, a single enterprise storage array could hold data for servers variously regulated by the Sarbanes-Oxley Act for corporate accounting, HIPAA for health benefits information, and PCI DSS for credit card processing. During an audit, storage systems must demonstrate controls to ensure that a server under one regime cannot access the storage assets of a server under another. Typically, eye-SKUZ-ee storage arrays explicitly map initiators to specific target WANs. An initiator authenticates not to the storage array, but to the specific storage asset it intends to use. However, because the target WANs for SCSI commands are expressed both in the eye-SKUZ-ee negotiation protocol and in the underlying SCSI protocol, care must be taken to ensure that access control is provided consistently. Confidentiality and integrity. For the most part, eye-SKUZ-ee operates as a clear text protocol that provides no cryptographic protection for data in motion during SCSI transactions. As a result, an attacker who can listen in on eye-SKUZ-ee Ethernet traffic can reconstruct and copy the files and file systems being transferred on the wire, alter the contents of files by injecting fake eye-SKUZ-ee frames, corrupt file systems being accessed by initiators, exposing servers to software flaws in poorly tested file system code. These problems do not occur only with eye-SKUZ-ee, but rather apply to any SAN protocol without cryptographic security. IP-based security protocols, such as IPsec, can provide standards-based cryptographic protection to this traffic, generally at a severe performance penalty. Industry implementation, operating system capability. The dates in the following table denote the first appearance of a native driver in each operating system. Third-party drivers for Windows and Linux were available as early as 2001, specifically for attaching IBM's IP Storage 200i appliance. A Euro target available only as part of Windows Unified Data Storage Server. Target available in Storage Server 2008. Target available for Windows Server 2008-02 as a separate download. Windows Server 2012 has built-in eye-SKUZ-ee target version 3.3. A Euro OS X has neither initiator nor target coming from vendor directly. There are a few OS X initiators and targets available, but they are from third-party vendors only. Targets. Most eye-SKUZ-ee targets involve disk, though eye-SKUZ-ee tape and medium changer targets are popular as well. So far, physical devices have not featured native eye-SKUZ-ee interfaces on a component level. Instead, devices with parallel SCSI or fiber channel interfaces are bridged by using eye-SKUZ-ee target software, external bridges, or controllers internal to the device enclosure. Alternatively, it is possible to virtualize disk and tape targets. Rather than representing an actual physical device, an emulated virtual device is presented. The underlying implementation can deviate drastically from the presented target, as is done with virtual tape library products. VTLs use disk storage for storing data written to virtual tapes. As with actual physical devices, virtual targets are presented by using eye-SKUZ-ee target software, external bridges, or controllers internal to the device enclosure. In the security products industry, some manufacturers use an eye-SKUZ-ee RAID as a target, with the initiator being either an IP-enabled encoder or camera. Converters and bridges. Multiple systems exist that allow fiber channel, SCSI and SAS devices to be attached to an IP network for use via eye-SKUZ-ee. They can be used to allow migration from older storage technologies, access to SANs from remote servers, and the linking of SANs over IP networks. An eye-SKUZ-ee gateway bridges IP servers to fiber channel SANs. The TCP connection is terminated at the gateway, which is implemented on a fiber channel switch or as a standalone appliance. See also. References. RFCs.